ready for takeoff.
Well, welcome to RubyConf. I'm really happy to be here. Nice to be in person. So today I'm going to talk about music, and specifically recorded music, and what kind of tricks producers and musicians use to make it sound good. And I'm going to explain that with a bunch of Ruby code. So what I like to do is use programming to understand the world. So the world is a very complicated place, and we are programmers. And we have this amazing tool to actually comprehend things, because if you write code, you actually have to know, you actually have to understand it, or otherwise you can't write the code. So it forces you to really learn it. And that's what I did with music. The music stuff I'm going to show to you today. So what I like to do is this process. So just don't understand it, try to write some code and fill for a while, and then at some point you kind of start getting it, and you end up with some hopefully simple code. And I'm going to show the outcome of this to you all today. So we're going to get started with a very brief history of the technology behind music that kind of was developed in the last 60 years, and that will bring us to digital audio, and that's where we can start using Ruby to actually see what's going on. So there are a bunch of code examples that go along with this talk. You can find those here. I will also post the slides after the talk, but if you want to follow it now, you can quickly go to this URL. So, what is music, actually? It's described by a couple of things. So, so audio, like what you're hearing right now, is a waveform that's sort of like moving through the air. So there's a whole bunch of air molecules bouncing into each other, and our ears perceive those and kind of make a model out of that. So a waveform is, the easiest way to visualize it is like this. It's basically the same as a wave in a pool of water, except with air molecules instead of water molecules. So these waves kind of travel through the air from a sound source to your ear. So in this case, there's a big speaker here, a bunch of speakers, and they create these waves, and then there are a bunch of little hairs in your ear called follicles that vibrate as these vibrations come in, and they generate a signal that's then processed in your brain, and that creates this sort of illusion of speech or what we call music. So there's nothing really inherently musical about.
Progress. 45 for preferred brand.
Oh. Okay. That's also audio. Yeah, so your brain generates, it has these models that kind of make sense of these incoming vibrations. And the neuroscientists don't really truly understand how this works yet. So there's some kind of magic going on that kind of turns these very simple patterns into something we call music. So how does the brain, what are the basic patterns that the brain uses to map this? So the first thing is pitch. So pitch is the amount of oscillations per second, or any given time span. If we go lower, you end up with a bassy instrument like a bass guitar, and higher up is like a violin. And the more oscillations per minute per second you have, the higher we perceive it to be. So basic pitch sounds like this. And if you use multiple pitches, you get a scale. So this is the one we're all familiar with. So this is the exact same shape of a waveform, only it happens less or more times per second. So the next thing is timbre. So timbre is all the little variations within the pitch that kind of create a vibe around the sound. So that would sound something like this. Oh, excuse me. is like a little thing from the Beatles they did in the 60s. So there's a single pitch here, but there's just a whole lot of detail to the sound because it's generated by a lot of different instruments that all have their own timbre. And finally, we have tempo. So tempo is created by silence, really. So this, if you introduce some silence in a fixed way in between actual waveforms, then you will get something that sounds like a rhythm. So a drum loop like this is like an example of tempo. And really it's about the silence. You know, the silence in between creates this illusion. Well, it's not really an illusion, but it creates this perception of something having a rhythm. So if you combine those things, you end up with like a little song. So if we just get the scale and we get some tempo, and we get a little bass. Yeah, it's almost nothing, but it's already like sort of like a song. So back in the day, music was always live, so there was no recorded music. And then sort of like technology happened. As we're well aware, like that changed the world in a number of different ways. And this led to recorded music. And we're just going to quickly go over like these sort of like these steps in technology that led us to digital audio today. So it all started with this guy. Thomas Edison. So he came up with like this device. So this is like a little roll, and if you shout really hard into that hole, it will vibrate like a little needle, a little bit, and that will etch a pattern into this wax cylinder in the middle. And once you play that back, you have like a very rudimentary sound device. So that sounds a little like this. So this wasn't a huge hit yet, and Thomas Edison had made one really big mistake, which led to this not being adopted. He really liked to patent stuff, so he had a patent on the cylinder, and therefore nobody could expand on the technology or like use it for themselves. So this ended up completely failing, and this other guy called Berliner came up with the idea of just using a cylinder. So maybe if Edison had not patented this, he used a disc. So maybe if Edison had not patented the cylinder, we would have been walking around with like these little cylinders for like 50 years instead of discs. And so it goes to show like patents are dangerous if you want your technology to be adopted. So these discs started sounding like a little bit better, but it was still quite bad. And then we got like this magnetic tape technology, and that sounded pretty good. So some people say like the technology never got better after this. This was sort of like the best thing, and it only got worse. Maybe they're right. So these tape decks really made like a lot of like stuff possible in the studio, and especially after the Second World War happened, like we got these tubes, and we got like multi-channel recording stuff. So and that really like created an industry of where recorded music actually became more important than live music. So it became a product, and people made these records and like mixed them on these desks like this. You know, we got transistors, and that brings us to the 80s, because in the 80s, like the whole music world turned digital. So up until then, everything was still really about a groove in a disc, for example, and it would actually be fully analog. But now we got the CD, and we got computers. So now, like these big studios of the past were kind of like, we got software that could just do the same thing. And nowadays you can get your little laptop and basically use all the tools that used to be available in the past in these big studios. So what we're going to do now is kind of dive into what digital audio actually is, and we're going to replicate a few of these tools that you see on the screen here now using Ruby with the goal of like better understanding what they do. So digital audio, it's a bunch of samples. So if you have a waveform, like this one, for example. Like on every corner in this diagram, a sample is being made. So it's basically measuring like how high the intensity of the signal is at that point. And if you use all those samples to, you can build that wave back up and play it. And you'll hear basically the same thing as the thing that you sampled. If you do it often enough, the human hearing is cannot perceive enough detail to actually know that it's been sampled. It's indistinguishable. So digital audio is a whole bunch of numbers in a row in a sequence that form those waveforms and allow us to play them back. So we got a bunch of tools and ways in Ruby of doing something with audio. So I picked for this presentation this gem. So this is the wave file gem that can write and read WAV files, which are basically just sequences of these samples. So we got a little code here, which is not super important, but this allows us to read back a wave file and just put it all in a very big array. So we have like one sequence of numbers to work with, which kind of makes other stuff simpler. And then you end up with this. So it's just a whole lot of numbers. So they're both positive and negative. So this waveform kind of oscillates around the zero. So parts of it are on the negative side of things, and parts of it are on the positive side of things. So this is kind of hard to do something with for a human, because it's just like random numbers, and we can't really make sense of that. So we're going to use another gem, chunky PNG, to like make some visualizations of what we're actually doing. So if we loop through these samples and we create an image and we just draw dots on that image, we end up with a visualization that looks a little like this. So this is some real-world audio, which looks pretty random. So like all these dots are just one of those samples from one of those waveforms. And if you do this visualization on a mathematically generated wave, then you actually end up with a very readable thing. So this is only maybe 10 milliseconds of audio that we're looking at here at the moment. So what we do next is we're going to group those samples into buckets, so we can look at some longer time frames and still see what's going on. And that code looks like this. Like if you this is all available on GitHub. So if you want to get into that, definitely check it out. So we end up with a visualization that looks like this. So if you've ever worked with any digital audio software, this probably looks familiar. So you'll see the intensity level of the waves basically right here. So now we can look at some stuff, and next up we can actually start modifying the audio as well using Ruby. So the first thing we're going to do is amplify the audio. So we're going to make it louder. That used to be done with tubes, with transistor amps, and we're going to do it with Ruby. So we got a piece of audio here. It sounds like this. That's already pretty loud, so I'm going to turn down the volume a little bit. And we want to amplify it so it's a little bit louder. So you can see that it's louder here because the peaks actually go up and down further than in the first sample. And the way we're going to do that is simply by multiplying every sample with some ratio. So we got samples that are say have a value of 5,000, and if we multiply them by 2.0, everything is going to be twice as loud, and that sounds like this. And I think that's sort of the theme that will come up more in this presentation, that actually a lot of this audio stuff is quite relatively simple math. We're doing nothing fancy here, and it actually does what we want. What could also happen is that we amplify something by too much. So if you, that's called clipping. So if we go outside of the range of what the floating point number we're using here can take, you end up cutting up the highest part of the waveform, and you end up with something that audio engineers hate. I'm sure the guys in the back know about this as well. And you get clipping, which sounds like this. And this is a form of distortion, which also became like a part of music. Because like if you think about like a guitar, like a heavy metal guitar sound, for example, that's basically like a pleasant way of clipping sounds. And in this case, you'll see here that the peaks of this waveform kind of go over the limit of what we can take, and that leads to this distortion effect. So the next thing we're going to discuss is mixing. So mixing used to be done, well, it's still done on these desks like this. They kind of like merge electronic currents. And if you want to mix stuff, you take multiple pieces of audio and you merge them together and you end up with a more complicated waveform. And in this case, we're going to take those two samples of those two pieces of audio at the top, and we're going to merge them into the more complicated one at the bottom. The way we do that is by summing them up. So we're reading like these three wave files, so they all have the same length. And if we loop through them all and simply sum up the numbers from each one of them and like create a new array, output array of them with like where every sample is summed up on the same position, you end up with this waveform. So this is like a Ruby mixed wave. So again, what you see here is that if you do the simple stuff correctly, then it actually just works, which kind of surprised me as I made this presentation, because like in theory I know that it's supposed to work like that, but if you actually just do the math, then you get the same result. So next up is compression. So compression is a trick audio engineers use to make stuff sound louder, basically. So you get rid of the peaks, so you can make the whole thing louder. So if you listen to stuff on the radio, like anything you listen to will be compressed. That used to be done by devices like this one in the past. We can do it with Ruby as well. So the basic principle is that if we have a waveform like this, we're going to choose a threshold for it. So we're going to pick a point where we think that the peaks that go beyond that point are too loud, and then we're going to like make those peaks less loud by just bringing down the volume only on those peaks. And next up, we can apply what's called makeup gain. So because we lowered the peaks, we are now able to just bump up the volume on all the samples without actually hitting this clipping limit that we saw earlier, and that will change the waveform. So we're starting with like these two cymbal hits. I'll let you hear them. Yeah, so we got those two cymbal hits, and what we're going to do is reduce the peaks on them. So we're looping through all the samples, and we're looking for all the samples that are above the threshold, and then we're making them less loud using a ratio. And if they're not above the threshold, we're just going to keep them as is. And then in the second pass, we're going to apply makeup gain, which is exactly the same thing as the amplification thing we used earlier. We're just going to make every sample louder now. And if you combine those two steps, you end up with like two methods feeding each other's output into each other. And we go from like this waveform to this shape. So if you look at the difference, you'll see that it's way less peaky. So like the sort of like the samples in the beginning, the peaks are kind of like toned down, and the softer part is actually louder, and that sounds like this. So this is probably the world's worst compressor, but it is a real compressor. And if you start to notice this, you'll hear this like everywhere, because like anywhere, especially in techno music, there's usually a lot of heavy compression going on. And you can kind of like detect that they're doing it by just listening to sort of like how things fade out. Like if a cymbal fades out naturally, it will end like quite quickly, and it will be a lot softer quite fast. And if it's compressed, then the sort of like tail end of the waveform is just going to be much longer. Yeah, and that's all there's to compression. And we're going to finish up with a bunch of ways of making sounds. So a lot of music nowadays uses synthesizers. So this is a Moog synthesizer, which is really a beast. So there's a lot of analog components in here. And this thing can do a bunch of different things. We're going to cover a couple of them. So the first thing we're going to cover is making noise. So if we want to make noise and, in Ruby, it's really not that hard, because we only have to use the random function to just generate a whole bunch of random samples. So we're just going to do this a bunch of times and just like get a number in this range and plot it and add it to the array. And if you visualize that, it looks like this. So noise is basically randomness, and we can get pretty close with Ruby, as close as you can on a computer. So this is some real Ruby-generated noise. And you might wonder, like, why do we need noise? Because it's noise, and nobody cares. But noise is actually used a lot in music production, because if you use silence to kind of like introduce a tempo, you end up with something like this. So these noise samples, if you cut them off and put silence in the middle, you end up with something that looks a lot like, sounds a lot like a snare drum. So this sound is being used for percussive sounds in a lot of electronic music. Next up is the square wave. So a square wave is one of the simplest ways of making a pitch. So a square wave sounds like this. It's very ugly, but if you do some processing, it might get better. So to do a square wave, we're going to create an oscillator in Ruby. So an oscillator is something that can generate these like rows of samples to get a certain sound. So we're going to make one using the enumerable module. So if you include enumerable and you implement each like this, you can just use this in all the other enumerable compatible things in Ruby, and easily generate some arrays. So if you look at the implementation of the next sample method here, this sample this generates new samples. So anytime we call it, we're incrementing the position by 1, and if the position is in a certain state, we're going to like generate a high positive number. If it's in the next state, we're going to generate a high negative number. So that way we get like an alternated sound in our sample. So we're going to call this oscillator like this. So we're creating a new one. We're creating an output array, and we're just going to call this oscillator a bunch of times and add it to the output. And then you end up with an image that looks like this. So you'll see that this is the reason it's called a square wave, is that like if you would draw vertical lines in this, you would end up with a whole bunch of squares. So this is one of the like core components of electronic music, even though it sounds horrible on its own. And the next one that's used a lot is the sine wave. And the sine wave looks like this. You can draw it using a circle, as this image demonstrates. So this is like a fundamental building block of a lot of sounds, actually all sounds. And the way we generate a sine wave is we use the math.syn function in Ruby, and we can use pi here to plot a position in this circle based on the position we have. And we can use that to generate samples again. And then we end up with a visualization like this, and it sounds like this. So this is a basic building block for basically all music. And we can also create a chord with these oscillators. So if we take 3 oscillators, and we pick different frequencies for all of them, and we combine those by doing the mixing trick we did earlier, and we just sum up those numbers, you end up with something that sounds like this. And this way you can generate any combination of notes which form chords that would be used in music as well. And if you're interested in this, it's cool to look at the Fourier transform. So what we were doing here is we were using multiple formulas to generate sine waves and combine those into a more complex waveform. But using the Fourier transform, you could like go back and kind of like deduce which sine waves generated this more complex waveform. And if you're doing anything with like pattern recognition in graphs or in metrics data, this is like a really cool thing to dive into. And finally, we can also generate some timbre using a computer. So if we take these oscillators again, and we take a sine wave and we take a square wave, and we mix those two together, you end up with like this weird looking wave shape, which sounds like this. So this is probably also like the ugliest timbre I've ever heard. But it demonstrates that we can, that in the end it all comes down to these very simple building blocks. And that brings me to the end of my presentation. But I can see that you guys are kind of skeptical that this is already possible. So I decided to make a cover of like my favorite song ever, using only the samples that I generated today. So here it is. Thank you.